Imagine, for a moment, that the universe is not just a vast, empty stage, but a symphony, a complex dance of tiny, vibrating strings. These strings, far smaller than atoms, far more fundamental than particles, are the building blocks of everything you see, touch, and experience. This is the mind-bending world of string theory, a quest to understand the very fabric of spacetime and answer some of the biggest questions in the cosmos. What are we made of? How does the universe work? And what happened before the Big Bang? Stick around, because we're about to dive into a world where the smallest things hold the biggest secrets. The genesis of string theory. String theory emerged from a desire to reconcile two pillars of physics: quantum mechanics and general relativity. These frameworks describe the universe at vastly different scales, with quantum mechanics governing the tiny world of particles and general relativity explaining the grand scope of galaxies and black holes. The incompatibility between these theories has been a thorn in the side of physicists for decades. Enter string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are incredibly small, on the order of the Planck length, which is about 1.6 x 10^35 meters. To put that into perspective, it's like comparing a standard basketball to the entire observable universe. The vibrations of these strings determine the properties of particles, much like the different notes played on a guitar string. This elegant idea offers a potential path to unifying the forces of nature, a goal that has eluded physicists for generations. At its core, string theory suggests that the universe is a symphony of vibrating strings. Each type of particle, electrons, quarks, photons, corresponds to a different vibrational mode of these strings. This is akin to how a single musical instrument can produce a variety of notes depending on how it is played. The beauty of this theory lies in its simplicity and its potential to explain a wide range of phenomena. For instance, the different frequencies of a guitar string produce different musical notes, just as the different vibrational modes of a string in string theory produce different particles. This analogy helps to visualize how a single, fundamental entity can give rise to the diverse particles we observe in nature. The theory also introduces the concept of extra dimensions, positing that the universe has more than the familiar three dimensions of space and one of time. These extra dimensions are compactified, or curled up, at scales too small for us to perceive directly. One of the most intriguing aspects of string theory is its ability to address some of the biggest questions in physics. For example, it offers a potential explanation for the nature of gravity, which has been a mystery since the days of Newton. In string theory, gravity arises naturally as one of the vibrational modes of the strings. This is a significant step towards unifying gravity with the other fundamental forces, electromagnetism and the strong and weak nuclear forces. Another big question that string theory tackles is the origin of the universe. By providing a framework that could describe the very earliest moments of the Big Bang, string theory offers insights into the initial conditions that led to the universe we see today. It also suggests that our universe might be just one of many in a vast multiverse, each with its own set of physical laws. This idea, while still speculative, has profound implications for our understanding of reality. String theory is not without its challenges. One of the main criticisms is that it is currently difficult to test experimentally. The energy scales at which string theory effects become significant are far beyond what our current technology can achieve. However, this does not diminish the theoretical appeal of the theory. It continues to inspire new ideas and approaches in physics, pushing the boundaries of our understanding. The quest to unify the fundamental forces of nature is one of the most ambitious endeavors in science, and string theory represents a bold step in that direction. Whether it ultimately proves to be the correct framework remains to be seen, but its impact on theoretical physics is undeniable. The journey to understand the fabric of spacetime is ongoing, and string theory is a vital part of that journey. Early developments in quantum mechanics. Quantum mechanics emerged from the need to explain phenomena that classical physics couldn't. At the turn of the 20th century, scientists like Max Planck and Albert Einstein introduced ideas that would shake the foundations of physics. Planck proposed that energy is quantized, meaning it comes in tiny, discrete packets called quanta. This was a radical departure from the smooth, continuous waves described by classical physics. Think of it like a guitar string. In classical physics, the string vibrates in a smooth wave. But in the quantum world, the string can only vibrate at specific frequencies, like the distinct notes on a guitar. This quantization is a fundamental aspect of quantum mechanics. One of the big questions that quantum mechanics sought to answer was the behavior of electrons and atoms. Classical physics suggested that electrons should spiral into the nucleus, causing atoms to collapse. But they don't. Niels Bohr proposed a model where electrons occupy fixed orbits, much like planets around the Sun, but with a twist. Electrons can jump between these orbits, absorbing or emitting energy in the process. This was a step towards understanding the structure of atoms. It's like a ladder. You can't stand in between the rungs. You have to be on one or the other. Similarly, electrons can't have just any energy. They must have specific, quantized energies. The early developments in quantum mechanics also brought about the concept of wave-particle duality. This idea, proposed by Einstein and later expanded by Louis de Broglie, suggests that particles can exhibit both wave-like and particle-like properties. It's like a coin that's both heads and tails at the same time, until you look at it. This duality is a cornerstone of quantum mechanics and has been confirmed by numerous experiments. For instance, electrons can interfere with each other like waves, but they can also be detected as discrete particles. This duality is crucial for understanding phenomena at the quantum scale. Another significant development was the formulation of the Schrödinger equation by Erwin Schrödinger. This equation describes how the quantum state of a physical system changes over time. It's a bit like a recipe that tells you how to prepare a quantum state. The solutions to this equation are wave functions, which contain all the information about the quantum system. The Schrödinger equation is fundamental to quantum mechanics and has wide-ranging applications, from explaining chemical bonds to describing the behavior of particles in a semiconductor. It's a powerful tool that helps us understand the quantum world. The need for a unified theory. Our understanding of the universe is like a grand symphony, with different instruments playing their own melodies. General relativity explains the grand, sweeping tunes of gravity and the cosmos, while quantum mechanics handles the intricate, high-pitched notes of the very small. But these two theories don't harmonize. They're like instruments playing in different keys, creating a discordant cacophony when brought together. This is where the need for a unified theory comes in, a theory that can bring all these disparate melodies together into a single, harmonious composition. Think of it like trying to describe a guitar string. You can describe its vibrations, the notes it plays, and the music it creates. But you can also describe its physical properties, like its tension, thickness, and the material it's made from. These are two different ways of looking at the same thing. Similarly, a unified theory would allow us to describe both the gravitational and quantum properties of the universe in a single framework. It's like having a sheet of music that shows both the individual notes and the overall harmony. String theory is one attempt at this unification. It proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings. Different vibrations of these strings give rise to different particles, like the notes on a guitar string. This is a profound idea because it suggests that all the seemingly disparate particles and forces in the universe are just different aspects of the same underlying reality. It's like realizing that a violin, a guitar, and a cello are all just different ways of playing the same fundamental concept, a stringed instrument. But string theory is notoriously complex. It requires extra dimensions beyond the familiar three of space and one of time. It also predicts the existence of many possible universes, each with its own set of physical laws. This might seem like a lot of baggage, but it's a small price to pay for a theory that could finally bring together the disparate melodies of our universe into a single, harmonious symphony. It's a bold attempt to answer some of the biggest questions we have. What is the universe made of? How did it begin? What are the fundamental laws that govern its behavior? String theory offers a tantalizing glimpse of a future where these questions might finally have answers. The birth of string theory. String theory emerged from a desire to reconcile two pillars of modern physics: quantum mechanics and general relativity. These frameworks describe the universe at vastly different scales, with quantum mechanics governing the tiny world of particles and general relativity explaining the cosmic dance of galaxies and black holes. The inconsistency between these theories has long puzzled physicists. String theory proposes a solution by suggesting that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are incredibly small, on the order of the Planck length, which is about 1.6 x 10^35 meters. To put that into perspective, it's like comparing a grain of sand to the size of the entire observable universe. The vibrations of these strings give rise to the different particles and forces we observe, much like the different notes produced by a guitar string depending on how it vibrates. The idea that everything is made of tiny, vibrating strings is a radical departure from traditional particle physics. In the Standard Model, particles are considered zero-dimensional points. But in string theory, they are one-dimensional strings that can vibrate at different frequencies. These vibrations correspond to different particles, such as electrons, quarks, and photons. It's akin to how a single musical instrument can produce a variety of notes. The beauty of this approach is that it naturally incorporates gravity, which has been a stubborn holdout in the quest for a unified theory. Gravity, in string theory, is not an exception but a natural consequence of the geometry of spacetime. This is a significant step towards answering some of the biggest questions in physics, such as what happened at the Big Bang or what lies at the center of a black hole. One of the most intriguing aspects of string theory is the concept of extra dimensions. Our everyday experience is limited to 3 spatial dimensions and 1 time dimension. However, string theory suggests that there could be up to 10 or 11 dimensions in total. These extra dimensions are compactified or curled up at scales too small for us to perceive directly. Think of it like a garden hose. From a distance, it appears as a one-dimensional line, but up close, you can see it's a 3-dimensional object with a circular cross-section. Similarly, the extra dimensions in string theory could be curled up so tightly that we don't notice them in our daily lives. This idea opens up a wealth of possibilities for understanding the fundamental nature of the universe. String theory also offers a potential framework for answering some of the most profound questions in physics, such as the nature of dark matter and dark energy. These mysterious components make up about 95% of the universe, yet we know very little about them. String theory could provide candidates for dark matter, such as stable, massive particles predicted by certain string models. Additionally, the theory's framework might offer insights into the nature of dark energy, which is driving the accelerated expansion of the universe. While these ideas are still speculative, they highlight the potential of string theory to address some of the biggest mysteries in cosmology. The journey to understand the fabric of spacetime is far from over, but string theory offers a promising path forward. Bosonic string theory. In the vast symphony of theoretical physics, bosonic string theory plays a foundational note. It's the simplest form of string theory, a framework where the point-like particles of particle physics are replaced by one-dimensional objects called strings. These strings vibrate at different frequencies, and their vibrations correspond to different particles, like notes on a musical instrument. In this theory, the strings are bosons, which are particles that follow Bose-Einstein statistics. They include force carriers like photons and gravitons, but notably, they don't include fermions, which are particles like electrons and quarks that make up matter. The fabric of space-time, in this context, is like a trampoline. When you place a heavy ball on it, the trampoline bends, and if you roll a smaller ball nearby, it will follow a curved path. Similarly, massive objects like stars and planets warp space-time, and other objects move along these curves, which we perceive as gravity. Bosonic string theory suggests that these strings interact with this fabric, their vibrations creating the very forces we experience. It's an elegant idea, but it's not without its challenges. For instance, the theory requires spacetime to have 26 dimensions, which is a tough pill to swallow. We only experience 4, 3 of space and 1 of time. One of the big questions bosonic string theory tries to tackle is the unification of forces. In our everyday world, we see 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. But at the most fundamental level, physicists suspect these are all manifestations of a single, unified force. Bosonic string theory attempts to tie these together, with gravity emerging naturally from the vibrations of closed strings. It's like trying to explain why different musical instruments can play the same note. But in this case, the instruments are the fundamental forces, and the note is the unified force. However, bosonic string theory is not without its limitations. It doesn't include fermions, which are crucial for describing matter. This is where supersymmetric string theory comes in, a more complex framework that introduces supersymmetry, a theoretical symmetry between bosons and fermions. But even with its limitations, bosonic string theory is a crucial stepping stone. It's like learning to play scales before attempting a concerto. It provides a simpler framework to understand the complex symphony of strings and spacetime. And who knows, perhaps one day, we'll find a way to incorporate fermions into this beautiful, vibrating tapestry. The first superstring revolution. The first superstring revolution marked a pivotal moment in theoretical physics, where the seemingly disparate worlds of quantum mechanics and general relativity began to intertwine in a way that promised to answer some of the universe's most profound questions. At its heart, string theory posits that the fundamental particles we observe are not zero-dimensional points, but rather one-dimensional strings that vibrate at different frequencies. These strings are incredibly tiny, on the order of the Planck length, which is about 1.6 x 10 carat 35 meters. To put that into perspective, it's like comparing a standard guitar string to the entire observable universe. The different vibrational modes of these strings give rise to the various particles we see, much like how different notes on a guitar string correspond to different musical notes. One of the most groundbreaking aspects of the first superstring revolution was the realization that string theory naturally incorporates gravity. In the standard model of particle physics, gravity is the odd one out, described by general relativity, while other forces are governed by quantum field theory. String theory, however, unifies all fundamental forces, including gravity, into a single framework. This is akin to finding a universal language that can translate between different dialects, bringing harmony to a previously fragmented linguistic landscape. The theory suggests that the graviton, the hypothetical particle that mediates gravity, is merely one of the many vibrational modes of the string. During this period, physicists also discovered that string theory has an astonishing number of possible solutions, each corresponding to a different possible universe with its own set of physical laws. This vast landscape of possibilities raises profound questions about the nature of reality and our place in the cosmos. It's as if the universe is a grand symphony, and string theory is the sheet music that contains all possible compositions. The challenge lies in deciphering which composition corresponds to our particular universe. Moreover, the first superstring revolution introduced the concept of supersymmetry, a theoretical framework that posits a partnership between bosons and fermions, the two types of fundamental particles. This symmetry could potentially solve some of the deepest mysteries in physics, such as the hierarchy problem and the nature of dark matter. The revolution also brought about a deeper understanding of the fabric of spacetime. In string theory, spacetime is not a smooth continuum, but has a fine-grained, foamy structure at the smallest scales. This is akin to zooming in on what appears to be a smooth surface, only to find a complex, textured landscape. The theory suggests that spacetime itself is dynamic and can change shape, much like a rubber sheet that can be stretched, bent, or twisted. This dynamic nature of spacetime is crucial for understanding phenomena like black holes and the early universe. Furthermore, the first superstring revolution laid the groundwork for dualities, which are relationships between seemingly different theories that reveal they are actually different aspects of the same underlying reality. These dualities have profound implications for our understanding of the universe and continue to be an active area of research. Calabi-Yau manifolds and compactification. In the vast symphony of string theory, Calabi-Yau manifolds play a crucial role, like the sheet music guiding the strings of a violin. These complex, multidimensional shapes are not just mathematical curiosities. They are the hidden backstage of our universe, influencing the very fabric of spacetime. Think of them as intricate origami, folded in such a way that they compactify or hide extra dimensions predicted by string theory. Our familiar four-dimensional spacetime, 3 dimensions of space and 1 of time, might just be a tiny slice of a much larger 10 or 11-dimensional reality. Compactification is the process where these extra dimensions curl up into tiny, unnoticeable sizes, much like a garden hose that looks like a thin line from far away, but is actually a complex, three-dimensional object up close. Calabi-Yau manifolds are the shapes that these extra dimensions take when they compactify. They are special because they preserve a property called supersymmetry, a theoretical symmetry between two classes of particles, bosons and fermions. This symmetry is a cornerstone of string theory, suggesting a deeper, underlying harmony in the laws of physics. The shapes of Calabi-Yau manifolds are not arbitrary. They can vary, and different shapes can lead to different physical laws in our four-dimensional world. This is akin to having a Rubik's Cube where each twist and turn can lead to a different color pattern. The specific shape of the Calabi-Yau manifold can determine the types of particles and forces we observe. For instance, the manifold's topology can influence the charges of particles, the strengths of forces, and even the number of generations of matter particles. This is why physicists are so interested in studying these manifolds. They could hold the key to understanding why our universe looks the way it does. Moreover, Calabi-Yau manifolds are not just static objects. They can change shape, a process known as moduli stabilization. This dynamic nature adds another layer of complexity to the story. The changing shapes can lead to different vacua, or stable states, of the universe. Each vacuum can correspond to a different set of physical laws, raising profound questions about the multiverse and the nature of reality. It's as if the universe is a vast library, and each Calabi-Yau manifold is a different book, each telling a unique story of physics. The challenge is to find the right book that describes our universe. Dualities in string theory. Dualities in string theory are like finding two different paths that lead to the same destination. They reveal that seemingly distinct theories or descriptions can be equivalent, just like a single melody can be played in different keys. This concept is not just a mathematical curiosity. It's a profound insight that helps physicists understand the fundamental nature of the universe. One of the most famous examples is T-duality, which shows that string theories defined on a small spatial circle of radius r and on a large circle of radius 1/ are actually the same. It's as if you have a guitar string that sounds the same whether it's short and tight or long and loose. This duality suggests that the size of the extra dimensions predicted by string theory might be unobservable, adding a layer of complexity to our understanding of spacetime. Another striking duality is S-duality, which relates strong coupling in one theory to weak coupling in another. Think of it like a seesaw. When one side is up, the other is down. In this case, when the interactions in one string theory become strong, they can be described by another theory where the interactions are weak. This is akin to having a flashlight that's bright in the dark but dim in the light, and vice versa. S-duality has been crucial in solving problems that were previously intractable, providing a new lens through which to view the strong interactions that govern much of the nuclear world. It's like having a decoder ring that translates one language into another, revealing hidden connections between different theories. These dualities are not just abstract ideas. They have practical implications for our understanding of the fabric of spacetime. For instance, they suggest that the universe might have a kind of self-similarity, where different scales or regimes are connected in non-obvious ways. This could be a clue to unifying the four fundamental forces of nature, a goal that has eluded physicists for decades. Dualities also hint at the possibility of a deeper, more fundamental theory that underlies string theory itself. It's like finding a single thread that weaves through multiple tapestries, revealing a hidden pattern. By studying these dualities, physicists hope to uncover the ultimate rules that govern the cosmos, answering some of the biggest questions about the nature of reality. T-duality. T-duality is a remarkable symmetry in string theory that relates two seemingly different descriptions of the same physical reality. It's like having two different maps that both accurately represent the same terrain, but with different scales or orientations. At its core, T-duality shows that a string theory defined on a small spatial circle of radius r is equivalent to another string theory defined on a large spatial circle of radius 1/r, with the string lengths and other parameters adjusted accordingly. This might seem counterintuitive, but it's a direct consequence of how strings propagate and interact in these spaces. Think of it like a rubber band stretched around a cylindrical object. If you make the cylinder very thin, the rubber band can wrap around it many times, but it can also vibrate in complex ways. Conversely, if you make the cylinder very thick, the rubber band can't wrap around it as many times, but it can still vibrate in similar ways. T-duality suggests that these two scenarios are physically equivalent, even though they look different. This symmetry has profound implications for our understanding of space-time and the fundamental nature of reality. One of the most intriguing aspects of T-duality is its connection to the fabric of space-time itself. In traditional physics, we think of space-time as a smooth, continuous backdrop for physical events. However, string theory suggests that space-time might be more like a complex, dynamic entity with a rich internal structure. T-duality reveals that this structure can be probed and understood in different ways, depending on the scale and context. It's as if space-time has hidden layers or dimensions that become apparent only when viewed through the right lens. T-duality also raises big questions about the nature of compactification, the process by which extra dimensions in string theory are curled up or hidden from our everyday experience. If a small circle and a large circle can be equivalent, what does that mean for the geometry and topology of spacetime? Could it imply that the universe has a more intricate and interconnected structure than we ever imagined? These are the kinds of deep, thought-provoking questions that T-duality helps us explore. It's a powerful tool for unraveling the mysteries of the cosmos and pushing the boundaries of our understanding. S-duality. S-duality is a profound and counterintuitive concept in string theory, a framework that attempts to unify quantum mechanics and general relativity. At its core, S-duality suggests that seemingly different theories or descriptions of the universe can be equivalent, much like how a single piece of string can be tied in different ways to create distinct knots, yet they all remain the same string. This duality implies that strong and weak forces can be interchangeable under certain conditions, a notion that challenges our classical understanding of physics. For instance, a theory describing a strong force might be mathematically equivalent to another theory describing a weak force, even though they appear vastly different. This idea is not just a mathematical curiosity. It hints at a deeper, more unified structure underlying the fabric of spacetime. One of the most striking examples of S-duality is found in the relationship between type IIB string theory and its strongly coupled counterpart, M theory. In type IIB string theory, the coupling constant, which determines the strength of the interactions between strings, can be varied. When this constant is small, the theory is weakly coupled, and the strings are the primary objects of interest. However, when the coupling constant is large, the theory becomes strongly coupled, and the strings dissolve into more complex, higher-dimensional objects called d-branes. Remarkably, the strongly coupled type IIB theory is equivalent to a different theory, M theory, which describes a world where these d-branes are fundamental. This equivalence is a manifestation of S-duality, showing that what appears to be a single theory can have multiple descriptions depending on the strength of the interactions. The implications of S-duality extend beyond the realm of theoretical physics. It raises profound questions about the nature of reality and the fabric of spacetime. If different theories can be equivalent under certain conditions, it suggests that the universe might be described by a single, overarching framework that encompasses all known forces and particles. This unified framework could potentially answer some of the biggest questions in physics, such as the nature of dark matter, the origin of the universe, and the ultimate fate of spacetime. Moreover, S-duality challenges our classical notions of causality and locality, as it implies that the universe might be interconnected in ways that are not immediately apparent. Just as a single string can be tied in different ways to create various knots, the universe might be woven from a single, underlying fabric that manifests in different forms depending on the conditions. In practical terms, S-duality provides a powerful tool for physicists to explore the behavior of strongly coupled systems. By leveraging the equivalence between different theories, researchers can gain insights into complex phenomena that would otherwise be intractable. For example, the properties of a strongly coupled quantum system can be studied by mapping it to a weakly coupled system, where calculations are more straightforward. This approach has been particularly useful in condensed matter physics, where strongly correlated electron systems exhibit complex behaviors that are difficult to understand. By applying the principles of S-duality, physicists can uncover the underlying mechanisms driving these phenomena, paving the way for new discoveries and technological advancements. In essence, S-duality is not just a theoretical curiosity. It is a gateway to a deeper understanding of the universe and the fabric of spacetime. U-duality. U-duality is a profound concept in string theory that reveals a deep connection between seemingly different physical theories. At its core, it suggests that certain theories are not as distinct as they appear, and under specific conditions, they can be transformed into one another. This idea is akin to having two different musical scores that, when played under the right conditions, produce the same symphony. The U in U-duality stands for universal, emphasizing its broad applicability across various aspects of string theory. One of the most striking examples of U-duality is the relationship between different string theories themselves. In the late 1990s, physicists discovered that the 5 consistent superstring theories known at the time were not independent, but were connected through dualities. This means that one theory at strong coupling, where the interaction between strings is intense, can be equivalent to another theory at weak coupling, where the interaction is feeble. Think of it like a rubber band. Stretch it too much, strong coupling, and it behaves differently than when it's loose, weak coupling. Yet, the underlying physics remains the same, just described in different terms. U-duality also plays a crucial role in understanding the fabric of spacetime. In string theory, spacetime is not a static backdrop, but a dynamic entity that can change and fluctuate. U-duality provides a way to explore these fluctuations by transforming complex problems into simpler ones. For instance, calculating the properties of a strongly coupled string theory might be intractable, but its dual theory at weak coupling could be much easier to handle. This is like solving a complex puzzle by flipping it over and seeing a simpler pattern. By leveraging U-duality, physicists can gain insights into the nature of spacetime and the fundamental forces that govern the universe. Moreover, U-duality has implications for some of the biggest questions in physics, such as the nature of black holes and the quest for a theory of quantum gravity. Black holes, for example, are extreme objects where the effects of gravity are so strong that they warp spacetime itself. U-duality allows physicists to study these objects by transforming them into more manageable configurations. This approach has led to significant advancements in understanding the microscopic structure of black holes and their entropy, which is a measure of their disorder. By unraveling these mysteries, U-duality brings us closer to answering fundamental questions about the universe and its underlying laws. The 5 superstring theories. In the vast symphony of theoretical physics, the 5 superstring theories stand out as distinct melodies, each with its unique rhythm and pitch. These theories are type first, type IIA, type IIB, heterotico, and heterotic, and they represent different ways to formulate the consistent quantum mechanics of strings. Think of them as different languages describing the same underlying reality, each offering a unique perspective on the fundamental workings of the universe. They all share a common thread: the idea that the fundamental particles we observe are not zero-dimensional points, but rather one-dimensional strings that vibrate at different frequencies. The type-first theory is unique among the 5, as it incorporates open strings, which have endpoints that can interact and form boundaries. This is akin to a guitar string that's plucked and allowed to vibrate freely. The other 4 theories, type IIA, type IIB, heterotico, and heterotic, deal primarily with closed strings, which are like loops of string that vibrate in a continuous circle. The heterotic theories are particularly interesting because they combine the properties of both bosons and fermions, 2 fundamental types of particles that make up our universe. It's like mixing the best of both worlds, creating a rich tapestry of possibilities. Each of these theories has its own set of symmetries and dimensional requirements. For instance, type IIB theory is chiral, meaning it distinguishes between left-handed and right-handed versions of particles, much like our hands are mirror images, but not identical. On the other hand, type first and heterotico theories are non-chiral, treating left and right symmetrically. These differences are crucial because they influence the types of particles and interactions that can exist within each framework. It's like choosing between different musical scales. Each scale has its own unique sound and emotional resonance. The 5 superstring theories also differ in their treatment of spacetime dimensions. While all require 10 dimensions for consistency, they compactify the extra dimensions in different ways. This compactification is akin to rolling up a garden hose. From a distance, it appears one-dimensional, but up close, you can see its two-dimensional surface. The way these extra dimensions are compactified can lead to different physical phenomena in the four-dimensional world we experience. This is why the search for a unified theory is so challenging and exciting. It's like trying to solve a complex puzzle where each piece offers a glimpse into the bigger picture. M-theory and the second superstring revolution. In the realm of theoretical physics, M-theory stands as a profound attempt to unify all fundamental forces and particles into a single framework. It emerged from the realization that the 5 distinct superstring theories, each with its own set of rules and symmetries, were merely different facets of a more encompassing theory. Think of it like a multifaceted gem. Each face appears unique, but they all belong to the same gemstone. M-theory suggests that these string theories are connected through various dualities, much like how different musical notes can be part of the same harmony. This unification is a significant step towards answering some of the biggest questions in physics, such as what happened before the Big Bang or what lies at the center of a black hole. The second superstring revolution brought about a paradigm shift in how physicists view the fabric of spacetime. It introduced the concept of branes, short for membranes, which are multidimensional objects that strings can attach to or vibrate within. In this context, our universe could be a 3D brane floating in a higher dimensional space. This idea is akin to a sheet of paper existing in a three-dimensional world. From our perspective on the paper, we might not perceive the full 3D space around us. The revolution also highlighted the role of non-perturbative effects, which are crucial for understanding the strong coupling regime of string theory. These effects are like the deep, underlying currents in an ocean. They shape the surface waves, but they are not always immediately visible. One of the most intriguing aspects of M-theory is its connection to holography. The ADS/CFT correspondence, a key development from the second superstring revolution, suggests that a theory of gravity in a higher dimensional anti-de Sitter, ADS, space can be equivalent to a quantum field theory without gravity on its boundary. This is like a hologram, where a 3D image is encoded on a 2D surface. The correspondence provides a powerful tool for studying strongly coupled systems, as problems in one theory can be mapped to problems in the other. For instance, it has been used to model quark-gluon plasma, and even to understand certain aspects of condensed matter systems. This duality is a testament to the deep and often surprising connections that M-theory reveals. M-theory also offers a potential resolution to the black hole information paradox, a long-standing puzzle in theoretical physics. The paradox arises from the conflict between quantum mechanics, which suggests that information should be conserved, and general relativity, which implies that information can be lost in a black hole. M-theory, through its holographic principle, suggests that the information is not lost but is instead encoded on the event horizon of the black hole. This is akin to a library where the books are not stored inside but are instead encoded on the library's walls. The resolution of this paradox is a significant step towards a more complete understanding of the universe. It shows how M-theory can provide insights into some of the most profound questions in physics. Branes and their role in string theory. Branes, short for membranes, are fundamental objects in string theory that can have various dimensions. Think of them as the stages upon which the strings of string theory perform their dance. Just as a guitar string vibrates to produce different notes, strings in string theory vibrate at different frequencies to create the particles that make up our universe. Branes can be thought of as the platforms or stages where these strings can end or be attached. They come in different types, with D-branes being particularly important. These are dynamic objects that can move and interact, playing a crucial role in the dynamics of string theory. In the vast landscape of string theory, branes are like the backstage crew of a grand theater. They can be open or closed, and their properties can influence the very fabric of spacetime. For instance, A brain can be a higher dimensional object that our three-dimensional universe is embedded within. This idea is part of the brain world scenario, where our universe is a three-dimensional brain, floating in a higher dimensional space. This concept helps address some of the big questions in physics, such as why gravity is so much weaker than other fundamental forces. If gravity can propagate through the higher dimensions while other forces are confined to our brain, it could explain the observed weakness of gravity. Brains also play a significant role in the concept of duality and string theory. Duality refers to the idea that different string theory frameworks are actually equivalent, just described in different ways. For example, in T-duality, the theory described by strings on a small compactified dimension is equivalent to the theory described by D-branes in a larger dimension. This is akin to having two different musical scores that produce the same symphony. Such dualities suggest that brains are not just incidental objects, but are deeply intertwined with the fundamental structure of string theory. They provide a way to explore the theory's non-perturbative aspects, which are otherwise difficult to study. The role of brains extends to cosmology and the early universe. In the brain inflation scenario, the collision of brains could have triggered the Big Bang, providing a novel perspective on the origin of our universe. This idea is still speculative, but it highlights the versatility of brains in addressing some of the most profound questions in physics. By studying brains, physicists hope to gain insights into the nature of spacetime, the origin of the universe, and the fundamental forces that govern it. The interplay between strings and brains continues to be a rich area of research, offering a glimpse into the deeper workings of the cosmos. The holographic principle. The holographic principle is a mind-bending idea that suggests our universe might be like a hologram, where all the information contained in a volume of space can be described by the information on its boundary. Think of it like a DVD. The 3D movie you see is encoded on a 2D surface. Similarly, the holographic principle proposes that everything happening in our 3D universe could be encoded on a 2D surface at its edge. This principle emerged from attempts to reconcile quantum mechanics with general relativity, two pillars of modern physics that seem to be at odds with each other. It's a bit like trying to fit a square peg in a round hole, and the holographic principle offers a potential way to bridge this gap. At its core, the holographic principle is about information. In physics, information is a measure of the number of possible states a system can be in. The principle states that the maximum amount of information that can be contained within a given region of space is proportional to the area of its boundary, not its volume. This is a radical departure from our everyday intuition, where we'd expect the amount of information to scale with volume. It's like realizing that a book's content isn't determined by its thickness, but by the size of its cover. This principle has profound implications for our understanding of black holes, the early universe, and the nature of spacetime itself. One of the most intriguing aspects of the holographic principle is its connection to black holes. When something falls into a black hole, it's lost to the outside universe. But according to quantum mechanics, information can't be destroyed. This leads to a paradox. The holographic principle offers a potential resolution. The information isn't lost, it's encoded on the black hole's event horizon, the boundary that marks the point of no return. It's like the information is written in invisible ink on the horizon, waiting to be decoded. This idea has sparked a lot of research and debate, as scientists try to understand the implications and test the principle. The holographic principle also offers a new way to think about the fabric of spacetime. In this view, spacetime isn't fundamental. Instead, it emerges from something more basic, like a 2D information structure. It's like a 3D movie that appears solid and real, but is actually just light and sound. This idea is still speculative, but it's a promising avenue for research. It could help us understand some of the biggest questions in physics, like what happened during the Big Bang, or what happens inside black holes. It's a bit like having a new pair of glasses that lets us see the universe in a different way. String theory and the fabric of spacetime. String theory is a framework in which the point-like particles of particle physics are replaced by one-dimensional objects called strings. These strings vibrate at different frequencies, and their vibrations correspond to the various particles we observe in nature. It's like a tiny, invisible guitar string, with each note it plays representing a different particle. The beauty of this idea is that it could potentially unify all the fundamental forces of physics, including gravity, into a single, elegant theory. This is a big deal because it's one of the most significant unsolved problems in physics today. The fabric of spacetime, on the other hand, is a concept that comes from Einstein's theory of general relativity. It's a four-dimensional continuum that intertwines the three dimensions of space with the one dimension of time. Think of it like a trampoline. If you place a heavy ball on it, the trampoline will bend and curve around the ball. In the same way, massive objects like stars and planets warp the fabric of spacetime, creating what we perceive as gravity. This is why planets orbit stars and why we stay grounded on Earth. Now, string theory suggests that the fabric of spacetime might be even more complex than we thought. In this theory, spacetime isn't just a smooth, continuous fabric. Instead, it's made up of tiny, vibrating strings. These strings are incredibly small, on the order of the Planck length, which is about 1.6 x 10 carat 35 meters. That's so small that it's practically impossible to imagine. But if string theory is correct, then these tiny strings are the fundamental building blocks of the universe. They're the tiny threads that weave the fabric of spacetime. One of the most intriguing aspects of string theory is that it requires extra dimensions beyond the familiar three dimensions of space and one of time. These extra dimensions are compactified, or curled up, to such a tiny size that we can't perceive them. It's like a garden hose. From far away, it looks like a one-dimensional line, but up close, you can see that it's actually a three-dimensional object with a circular cross-section. In the same way, string theory suggests that our universe might have more dimensions than we can see. These extra dimensions could be curled up so tightly that they're invisible to us. This idea raises profound questions about the nature of reality and the structure of the universe. It's a reminder that there's still so much we don't understand, and so much more to discover. Spacetime as an emergent phenomenon. In the grand tapestry of the universe, spacetime is often considered the fabric that weaves together the very essence of reality. Yet, what if this fabric isn't fundamental, but rather a phenomenon that emerges from something even deeper? This is the intriguing idea behind the concept of spacetime as an emergent phenomenon. At its core, this notion suggests that the smooth, continuous fabric of spacetime we observe might actually arise from the intricate interplay of more fundamental, discrete entities. Think of it like a high-definition image on a screen. Up close, you see individual pixels, but from a distance, those pixels blend together to form a seamless picture. Similarly, spacetime might be a kind of pixelated structure when viewed at the smallest scales, but it appears smooth and continuous at the scales we experience in everyday life. One of the most compelling frameworks exploring this idea comes from string theory. In string theory, the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to the various particles and forces we observe. In this context, spacetime itself could be an emergent property of the complex interactions between these strings. Imagine a vast orchestra where each string is a musician. The music they create, the harmonies and rhythms, is analogous to the fabric of spacetime. The individual notes, or strings, might be discrete and distinct, but together they produce a continuous, flowing symphony that we perceive as spacetime. This perspective raises profound questions about the nature of reality. If spacetime is emergent, what lies beneath it? What are the fundamental entities that give rise to this phenomenon? These questions touch on some of the biggest mysteries in physics, including the nature of quantum gravity, the unification of quantum mechanics and general relativity, and the ultimate structure of the universe. For example, if spacetime is emergent, it might help resolve the long-standing conflict between quantum mechanics, which describes the behavior of particles at the smallest scales, and general relativity, which describes the behavior of spacetime at the largest scales. By understanding spacetime as an emergent phenomenon, physicists hope to bridge these two pillars of modern physics and gain a deeper understanding of the universe. Moreover, the idea of emergent spacetime has implications for our understanding of black holes and the early universe. In black holes, the fabric of spacetime is warped to an extreme degree, and the concept of emergence might provide insights into the nature of the singularity at the center of a black hole. Similarly, in the early universe, when the cosmos was incredibly hot and dense, the emergent nature of space-time could offer clues about the initial conditions that led to the universe we see today. By exploring these ideas, physicists are pushing the boundaries of our understanding and inching closer to answering some of the most fundamental questions about the nature of reality. The role of strings in space-time structure. Strings, in the context of string theory, are not the strings you'd find on a guitar or a tennis racket. They're tiny, one-dimensional, vibrating entities that, according to some theories, are the fundamental building blocks of the universe. These strings are incredibly small, on the order of the Planck length, which is about 1.6 x 10 carat 35 meters. That's so small that it's practically impossible to imagine. To put it into perspective, a string is to an atom what an atom is to the entire observable universe. These strings vibrate at different frequencies, and these vibrations determine the properties of the particles they form. It's like how different musical notes are produced by the same instrument, just vibrating at different frequencies. Now, space-time is the fabric that makes up the universe, combining the three dimensions of space with the fourth dimension of time. It's not a static, unchanging backdrop, but rather a dynamic entity that can bend, stretch, and warp. This is what Einstein's theory of general relativity tells us. But string theory takes this a step further. In string theory, space-time isn't just a stage for particles to act out their roles. Instead, the strings themselves are the actors, and their vibrations and interactions create the drama of the universe. The structure of space-time is deeply intertwined with the behavior of these strings. Think of space-time as a giant, invisible trampoline. When you place a heavy ball on it, the trampoline bends and warps around the ball. This is similar to how massive objects, like stars and planets, warp space-time. Now, in string theory, these strings are like tiny, vibrating rubber bands on the trampoline. Their vibrations cause ripples and disturbances in the fabric of space-time. These ripples can manifest as gravitational waves, which have been observed by experiments like LIGO. So, the strings don't just exist within space-time, they actively shape and influence it. Moreover, string theory suggests that there might be more to space-time than the four dimensions we're familiar with. It proposes the existence of additional hidden dimensions, compactified or curled up at scales too small for us to perceive directly. These extra dimensions could be crucial for understanding the fundamental nature of the universe. For instance, they might help unify the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces, into a single, consistent framework. This is one of the big questions that string theory aims to address. By studying the role of strings in space-time structure, we might unlock secrets about the very fabric of reality. Non-perturbative effects and space-time geometry. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings can vibrate at different frequencies, and their various modes of vibration correspond to different particles, like notes on a guitar string. Now, let's dive into the fascinating world of non-perturbative effects and their influence on space-time geometry. Non-perturbative effects in string theory are those that cannot be described by small perturbations around a fixed background. They are like the deep, resonant notes on a guitar that can't be captured by gently plucking the strings. These effects often involve strong coupling, where the interactions between strings are intense, and they can lead to significant changes in the geometry of space-time. One of the most striking examples is the appearance of D-branes, which are higher-dimensional objects where open strings can end. D-branes can have a profound impact on the shape and structure of space-time, much like how a heavy weight would distort a trampoline. Consider the case of a D3 brane, a three-dimensional object in string theory. It can wrap around certain directions in space-time, effectively compactifying them. This is akin to taking a long, straight hose and coiling it up, making it appear much shorter. The compactification changes the effective geometry of space-time, much like how the coiled hose has a different shape than the straight one. These non-perturbative effects can also lead to the creation of black holes and other exotic objects, further altering the space-time geometry. It's like how a powerful magnet can distort the shape of a flexible metal object, creating new and unexpected forms. Moreover, non-perturbative effects can give rise to phenomena like T-duality and S-duality. T-duality is a symmetry that relates string theories with different spacetime geometries. It's like discovering that two seemingly different musical instruments can produce the same note when played in a certain way. S-duality, on the other hand, relates strong coupling in one theory to weak coupling in another, showing that what seems strong in one context can be weak in another. These dualities reveal deep connections between different string theories and their respective spacetime geometries, much like how different languages can express the same idea. They also hint at a more fundamental, underlying theory that encompasses all of these dualities, a theory that might one day answer some of the biggest questions in physics, like the nature of dark matter or the origin of the universe. Black holes and string theory. Black holes, those cosmic vacuum cleaners, have always been a puzzle. They warp spacetime so much that not even light can escape. String theory, on the other hand, is a framework where the fundamental particles aren't zero-dimensional dots, but tiny, vibrating strings. It's like comparing a dust particle to a tiny guitar string. Now, when these two concepts collide, things get really interesting. In string theory, black holes aren't just simple, smooth objects. They're more like intricate, vibrating strings that can take on different shapes and forms. Think of them as different musical notes played on those tiny guitar strings. This is a big deal because it might help us understand what happens to information that falls into a black hole. You see, black holes seem to break a fundamental rule of physics. Information can't be created or destroyed, only transformed. But if information goes into a black hole and nothing comes out, where does it go? String theory offers a possible answer. The different vibrational states of the strings could encode the information, preserving it even as the black hole evaporates. Moreover, string theory introduces higher-dimensional objects called branes. Picture them as membranes floating in a higher-dimensional space. Black holes could be created when these branes collide or interact. It's like two pieces of fabric brushing against each other and creating a tiny tear. This idea could explain why black holes have mass, charge, and spin. Each of these properties could correspond to different types of branes or different ways they interact. But here's the kicker. String theory also suggests that black holes might not be as black as we thought. They could emit radiation, slowly losing mass and eventually evaporating. This is known as Hawking radiation, named after the physicist Stephen Hawking. It's a tiny effect, but over time, it could make black holes disappear. This raises big questions. If black holes can evaporate, what happens to all the stuff that fell into them? Does the information get destroyed, or does it somehow escape? String theory is still trying to provide answers to these profound questions. It's a work in progress, but it's a fascinating journey into the very fabric of our universe. Information paradox and its resolution. The information paradox, also known as the black hole information paradox, is a problem that arises when considering the nature of black holes and the fundamental laws of physics. At its core, the paradox questions what happens to information about the physical state of objects that are consumed by a black hole. According to the principles of quantum mechanics, information cannot be destroyed, but black holes seem to violate this rule. When matter falls into a black hole, it appears to lose all its information, seemingly disappearing from our universe. This poses a significant challenge to our understanding of the universe's fundamental laws. To grasp the essence of the paradox, think of a black hole as a cosmic vacuum cleaner. When it sucks up matter, it's like shredding a complex piece of music into tiny, indistinguishable pieces. The question is, can the original music be reconstructed from these pieces? According to quantum mechanics, the answer should be yes, but according to general relativity, the answer seems to be no. This contradiction is what makes the information paradox so perplexing. It's like trying to fit a square peg into a round hole, where the peg is the principle of information conservation, and the hole is the behavior of black holes. String theory offers a potential resolution to this paradox. In string theory, the fundamental particles are not zero-dimensional points, but tiny, one-dimensional strings that vibrate at different frequencies. These strings can vibrate in a multitude of ways, giving rise to the various particles we observe in nature. When a string falls into a black hole, it doesn't disappear. Instead, it can escape through the black hole's event horizon, carrying information with it. This process is akin to a magician's trick where the magician seems to make something disappear, but in reality, it's just hidden or transformed. The information isn't destroyed, it's just encoded in a different form. Moreover, string theory suggests that the fabric of spacetime itself is not smooth and continuous, but has a tiny, foamy structure at the smallest scales. This foaminess could allow information to leak out of black holes in a way that's consistent with quantum mechanics. Think of it like a sponge. If you pour water into a sponge, it seems to disappear, but it's actually being absorbed and stored within the sponge's structure. Similarly, information falling into a black hole isn't destroyed, but is stored and eventually re-emitted. This resolution aligns with the big questions about the nature of reality, suggesting that our universe is far more complex and interconnected than it appears. It also highlights the profound interplay between different branches of physics, offering a glimpse into the deeper, underlying structure of the cosmos. String theory and the early universe. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are incredibly small, on the order of the Planck length, which is about 1.6 x 10^35 meters. The different modes of vibration of these strings correspond to the different particles we observe in nature, like electrons, photons, and quarks. It's a bit like how different musical notes are produced by the same instrument, just vibrating at different frequencies. This idea is a radical departure from the standard model of particle physics, which treats particles as zero-dimensional points. In the early universe, conditions were extreme, with incredibly high temperatures and densities. This environment was a perfect crucible for testing the limits of our physical theories. String theory suggests that under these conditions, the fundamental strings could have interacted in ways that are very different from how they do today. For instance, the extra dimensions predicted by string theory might have been more accessible, allowing for interactions that are currently beyond our reach. Think of it like a tangled ball of yarn. In normal conditions, the strings are like individual threads, but in the early universe, they might have been more like a tightly packed, interconnected web. One of the big questions string theory aims to answer is what happened during the earliest moments of the universe, right after the Big Bang. Traditional theories struggle to describe this period because the conditions were so extreme that quantum effects would have been as important as gravitational effects. String theory, with its unique framework, might provide a way to bridge these two realms. It's like trying to describe a symphony where both the individual instruments and the overall harmony are crucial. In this analogy, the instruments represent quantum effects, and the harmony represents gravity. Moreover, string theory offers a potential explanation for the initial conditions of the universe. It suggests that the universe might have been born with certain properties, like a particular shape or size, due to the way the fundamental strings were vibrating. This is a bit like how a guitar string, when plucked, will naturally vibrate at certain frequencies. The initial conditions would then influence the evolution of the universe, leading to the structure we see today. However, it's important to note that string theory is still a work in progress. While it's a powerful and elegant framework, it's not yet a complete theory of everything. There are still many open questions and challenges to be addressed. Cosmic inflation and string cosmology. Cosmic inflation is a theory that attempts to explain the rapid expansion of the universe right after the Big Bang. Think of it like a balloon being inflated at an incredible speed. In a fraction of a second, the universe expanded exponentially, smoothing out any irregularities and setting the stage for the universe we see today. This rapid expansion is crucial for understanding the large-scale structure of the cosmos. It helps explain why the universe looks so uniform on the largest scales. Without inflation, the differences in temperature and density we observe wouldn't make sense. It's like stretching out a crumpled piece of paper until it's smooth. The wrinkles become so spread out that they're barely noticeable. String cosmology, on the other hand, is a branch of string theory that applies the principles of string theory to cosmology. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings vibrate at different frequencies, and their vibrations give rise to the various particles and forces we observe. In string cosmology, these strings play a crucial role in shaping the universe. They can form cosmic strings, which are one-dimensional defects in spacetime. These cosmic strings can have profound effects on the structure and evolution of the universe. They can act like seeds for galaxy formation, influencing the distribution of matter on the largest scales. The interplay between cosmic inflation and string cosmology is a fascinating area of research. Inflation provides a mechanism for the rapid expansion of the universe, while string theory offers a framework for understanding the fundamental nature of matter and energy. Together, they can help us address some of the biggest questions in cosmology. For example, what caused the Big Bang? What is the nature of dark matter and dark energy? How did the universe evolve to its current state? By combining these two theories, scientists hope to gain a deeper understanding of the fabric of space-time and the fundamental laws that govern our universe. It's like trying to unravel a complex tapestry where each thread represents a different aspect of the cosmos. By pulling on the right threads, we can start to see the bigger picture. String theory landscape and the multiverse. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings, incredibly small, far smaller than anything we can currently observe, oscillate at different frequencies, giving rise to the various particles and forces we observe in nature. Think of them like the strings on a guitar. Each string can vibrate in different ways, producing different notes. Similarly, the different vibrations of fundamental strings give rise to different particles, like electrons, quarks, and photons. This is a profound shift from the traditional particle physics model, which treats particles as zero-dimensional points. Instead, strings are one-dimensional objects, and their vibrations are what create the rich tapestry of the universe. The landscape of string theory refers to the vast number of possible configurations these strings can take. Each configuration corresponds to a different possible universe, with its own set of physical laws and constants. This landscape is not just a theoretical abstraction. It's a direct consequence of the mathematics of string theory. The number of possible configurations is staggeringly large. Some estimates suggest there could be as many as 10^500 different possible universes. To put that into perspective, that's more than the number of atoms in the observable universe. Each of these universes could have different dimensions, different forces, and different particles. Some might even have different numbers of dimensions. This idea is not just speculative, it's a natural outcome of the equations that describe string theory. The concept of the multiverse arises from the idea that our universe is just one of many possible universes within this vast landscape. In this view, the multiverse is a collection of bubble universes, each with its own unique set of physical laws. These universes could be connected in a complex web, with some universes giving birth to others through a process of eternal inflation. This idea is not unique to string theory. It's also a feature of other theories in cosmology, like the inflationary multiverse. However, string theory provides a specific framework for understanding how these different universes could arise and what their properties might be. The multiverse is not just a philosophical concept, it's a testable idea. Scientists are actively looking for evidence of other universes, such as patterns in the cosmic microwave background radiation that could indicate collisions between universes. The implications of the string theory landscape and the multiverse are profound. If true, it means that our universe is just one of many possible universes, each with its own unique set of physical laws. This raises deep questions about the nature of reality and our place in the universe. It also challenges our understanding of the fine-tuning of the universe. Why are the constants of nature just right for life to exist? In a multiverse, it's possible that most universes are inhospitable to life, but we just happen to live in one of the rare universes that is suitable. This idea is known as the anthropic principle. It's a controversial idea, but it's one that is actively being explored by scientists. The string theory landscape and the multiverse are not just abstract concepts. They are active areas of research that could fundamentally change our understanding of the universe. Experimental evidence and challenges. String theory suggests that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are incredibly small, on the order of the Planck length, which is about 1.6 x 10^35 meters. The different vibrational modes of these strings give rise to the various particles we observe in nature. It's like a cosmic symphony where each string is an instrument, and its vibrations are the notes that create the music of the universe. This idea is elegant and mathematically rich, but it also presents significant challenges, especially when it comes to experimental evidence. One of the biggest hurdles in testing string theory is the scale at which these strings are thought to exist. The Planck length is so small that our current particle accelerators, like the Large Hadron Collider, are nowhere near powerful enough to probe it directly. It's like trying to detect a single thread in a vast tapestry from a mile away. Indirect evidence might be possible, though. Some versions of string theory predict the existence of supersymmetric particles, which could be detected in high-energy experiments. However, despite extensive searches, no such particles have been found yet. This doesn't necessarily disprove string theory, but it does add to the mystery. Another challenge is the landscape problem. String theory suggests that there are a vast number of possible ways the strings can vibrate, leading to a multitude of possible universes, each with its own set of physical laws. This is akin to having a musical instrument that can play an infinite number of songs, but we only hear one. The landscape problem makes it difficult to pin down which version of string theory, if any, describes our universe. It's a bit like trying to find a specific grain of sand on a beach that stretches for miles. Despite these challenges, there are ongoing efforts to find experimental evidence for string theory. One approach is to look for signatures of extra dimensions. String theory often requires more than the 4 space-time dimensions we experience, 3 of space and 1 of time. These extra dimensions could be compactified or hidden in some way, but they might still have observable effects. For example, they could influence the way gravity behaves at very small scales. Scientists are also exploring the possibility of detecting cosmic strings, which are hypothetical one-dimensional defects in spacetime that could have formed in the early universe. These cosmic strings could produce unique gravitational wave patterns or affect the cosmic microwave background radiation. While these avenues are speculative, they represent some of the most promising paths forward in the quest to test string theory. Future directions in string theory research. String theory, with its elegant framework of tiny, vibrating strings, has long been a contender for a theory of everything, aiming to unify quantum mechanics and general relativity. Yet, despite its promise, it faces significant challenges, particularly in its lack of direct experimental evidence. Future research in string theory is focusing on several key areas to address these issues and push the boundaries of our understanding. One exciting direction is the exploration of string theory's landscape. This isn't a physical landscape, but a vast, multidimensional space of possible vacuum states, each corresponding to a different universe with its own set of physical laws. Think of it like a vast library, where each book is a different universe, and the shelves are the dimensions of the landscape. By studying this landscape, researchers hope to find clues about why our universe has the properties it does, and perhaps even find signatures of other universes. This could help answer big questions, like why the constants of nature seem fine-tuned for life, or whether there are other universes out there. Another promising avenue is the development of string theory's mathematical tools. String theory is deeply connected to advanced mathematics, and often, progress in one area fuels progress in the other. Researchers are working on improving our understanding of mathematical structures like Calabi-Yau manifolds, which are the extra dimensions curled up so small that we can't perceive them. These manifolds play a crucial role in string theory, determining the properties of the universe we see. By better understanding these structures, we can gain insights into the fundamental nature of reality. It's like trying to understand the shape of a garden hose by studying the patterns of water droplets it sprays out. Moreover, string theory researchers are increasingly collaborating with scientists in other fields, like condensed matter physics and quantum computing. These collaborations can lead to unexpected breakthroughs. For instance, ideas from string theory have already found applications in understanding high-temperature superconductors and quantum entanglement. By looking at these big questions from different angles, we might find new ways to test string theory or even discover new physics along the way. It's a bit like trying to solve a complex puzzle by looking at it from different perspectives, each time noticing new details that were previously invisible. As we wrap up our journey through the cosmic symphony of strings, let's recap the key points that have danced before us. We've seen how tiny, vibrating strings might be the fundamental building blocks of everything, from the atoms in your coffee to the galaxies swirling in the night sky. These strings, far smaller than anything we can imagine, hum and shiver in a grand cosmic concert, creating the music of the universe. And just like different musical notes, different vibrations of these strings could give rise to the particles and forces that shape our reality. We've also explored how these strings might weave the very fabric of spacetime itself. Imagine spacetime as a vast, multidimensional loom, and the strings as the threads that create the tapestry of our universe. This idea could help us unify the two great theories of physics, general relativity and quantum mechanics, into a single, elegant framework. But perhaps the most thrilling part of this journey is the big questions that string theory helps us grapple with. Why is our universe the way it is? Are there other universes out there, with different rules and different strings? Could string theory be the key to understanding the very essence of reality? As you step away from this video, take a moment to look around you. The chair you're sitting on, the device you're holding, even the air you're breathing. All of it could be a symphony of strings, playing the music of the cosmos. It's a humbling thought, isn't it? That we're all part of something so vast, so intricate, and so beautifully interconnected. If you've enjoyed this dive into the fabric of space-time, first I'd love to hear your thoughts. What's the most mind-blowing idea you've taken away from this? What questions do you still have? Share your thoughts in the comments below, and let's keep the conversation going. And if you're hungry for more cosmic adventures, be sure to subscribe to our channel. In our next video, we'll be exploring another mind-bending concept, the idea of a multiverse. Could there be other universes out there with different laws of physics, different histories, and maybe even different versions of you? It's a journey you won't want to miss. Until then, keep wondering, keep questioning, and keep looking up at the stars. After all, you never know what secrets they might be whispering to you.